Understanding the sklearn linear model, Perceptron. The sklearn linear model, Perceptron is a classic machine learning algorithm used for binary classification. It's a simple yet powerful model inspired by the biological neuron, capable of learning linear decision boundaries to separate data points into two classes. How it works. 1. Initialization. The perceptron starts with random weights for each feature and a bias term. 2. Data iteration. The algorithm iterates over the training data, one sample at a time. 3. Prediction. For each sample, the weighted sum of features plus the bias is calculated. This is called the net input. 4. Activation function. The net input is passed through a step function, also known as the activation function. This function determines the output of the perceptron, which is either 1 predicted class 1 or 0 predicted class 0. 5. Error calculation. The output is compared to the actual class label. If the prediction is incorrect, the weights are updated to minimize the error. 6. Weight update. The weight update rule is based on the error and the feature values of a misclassified sample. 7. Convergence. The training process continues until the perceptron converges, meaning the weights no longer change significantly or a predefined number of iterations is reached. Key aspects of the perceptron. Linear decision boundary. The perceptron learns a linear hyperplane in the feature space that separates the data into two classes. This means it can only handle linearly separable data. Binary classification. It's primarily used for classifying data into two categories. Sensitivity to data scaling. The perceptron can be sensitive to the scale of features. Feature scaling is recommended for optimal performance. Convergence. The perceptron is not guaranteed to converge if the data is not linearly separable. Key parameters in sklearn linear model, perceptron. YAML representation for key parameters. YAML. Perceptron. Penalty. Description. The penalty regularization term to be added to the loss function. L2 adds a squared penalty to the weights. L1 adds a penalty proportional to the absolute value of the weights. And elastic net combines both L1 and L2 penalties. Values L2, L1. Elastic net. None. Alpha. Description. Strength of the penalty, with higher values imposing stronger regularization. This is only relevant if a penalty is specified. Type float. Fit intercept. Description. Whether to calculate the intercept for this model. If set to false, no intercept will be used in calculations, i.e. data is expected to be centered. Type bool. Maxiter. Description. Maximum number of passes over the training data. Set to none for unlimited iterations. Type int. Toll. Description. The stopping criterion for the weights. The training will stop when the weights change by less than this amount in a given iteration. Type float. Shuffle. Description. Whether to shuffle the training data before each epoch. This can help with convergence and avoid local optima. Type bool. Random state. Description. The seed of the pseudo-random number generator to use when shuffling the data. This allows for reproducible results. Type int. Ether 0. Description. The learning rate for weight updates. This determines the step size during training. Type float. Warm start. Description. When set to true, reuse the solution of the previous call to fit as a starting point. Useful for online learning where data arrives in chunks. Type bool. Class weight. Description. Weights associated with classes in the form class label weight. This can be used to handle imbalanced datasets where certain classes are underrepresented. Type dict. Example usage in Python. Python. From sklearn linear model import perceptron. From sklearn datasets import load iris. From sklearn, model selection, import train test split. Load data. Iris load iris. X iris. Data. 2 select 2 features for visualization. Y iris, target 0. ASTI paint classify iris setosa vs. The rest. Split data into train and test sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Create and train the Perceptron model. Model Perceptron random state 42. Model. Fit X train. Y train. Make predictions on the test set. YPRED model. Predict X test. Evaluate the model's performance. From sklearn, metrics import accuracy score. Accuracy score test. YPRED. Print F accuracy point 2F. Limitations. Linearity. The perceptron cannot handle non-linearly separable data. Sensitivity to noise in the data can affect the accuracy of the model. Overfitting. The perceptron can overfit to the training data, especially if the number of features is high. Advantages. Simplicity. The perceptron is easy to understand and implement. Fast training. It is computationally efficient for training. Good for initial exploration. It can provide a baseline for more complex models. Use cases. Binary classification, classifying data into 2 categories, such as spam detection, fraud detection, or image classification. Linearly separable data, when the data can be easily separated by a linear boundary. Quick and simple solutions when you need a fast and straightforward model for initial analysis. Extensions. Multilayer perceptron, a network of perceptrons with multiple hidden layers, capable of learning nonlinear decision boundaries. Support vector machines SVMs, a more powerful algorithm that can handle nonlinear data and is less prone to overfitting. In conclusion, the sklearn linear model perceptron is a fundamental building block in machine learning, offering a straightforward approach to binary classification. Understanding its capabilities and limitations is essential for selecting the right algorithm for your task.